Hello, I welcome you all in this lecture series of matrix algebra that we are doing for quite a while now. This is the seventh lecture in the series, and today's topic that we are going to take is the diagonalization of matrices. Okay, and it is an important topic as such because you see in math physics most often you will find that we need the this kind of thing. So basically we need uh, diagonalization of matrix to be done. Diagonalization of matrices. Okay, and without wasting time, let us start. Okay, uh, as you're aware that for a diagonal matrix, I told you for a diagonal matrix, all the eigenvalues, all the eigenvalues lie on the diagonal side, right? On the diagonal. Okay, so all the value lie on the, or you can say all the eigenvalues are nothing but they are the diagonal elements. All the eigenvalues are the diagonal elements. So it would be interesting if somehow via some transformation we are able to reduce a matrix to a diagonal matrix. So if a matrix is given to us, it would be good if we can diagonalize it. If we can diagonalize it means what? I can bring my matrix in the diagonal form. I can bring my matrix in the diagonal form where the elements on the diagonal entries are nothing but the eigenvalues of A. Okay. So I hope people have joined in. Kindly mark presence once you join in so that that becomes convenient for me. Okay. So this particular transformation by means of which matrix A is transformed into a diagonal matrix is called as the similarity transformation. Is called as the similarity transformation. It is called as the similarity transformation. Okay. So suppose we have this eigenvalue problem which is given by Ax equals to lambda x. Okay. Let us say we have a problem, eigenvalue problem given as Ax is equals to lambda x. Here, let's say A is of, let us say A is of order n cross n. So I'll write, let's say A is of order n. Okay. Let us say that A is of order n, and what we want to do, I mean, at times, in physics, it is easier to change the variables. Okay, it is easier to change the variables in order to ease our original problem, in order to ease our original problem. And this is precisely what we are going to do today. This is precisely what we are going to do today. Okay. Now you see, let us introduce a change of variable, and let us say that your x is equals to some p times y. Let us say, or I can write in caps only. So let's say x is equals to p times y. Okay, what I am doing, at times it is, in physics also, in maths also, if your problem is not getting solved using some particular way, what we do, we start substitution. We use substitution, and if you use substitution, instead of x, if I'm using py, it will be like apy here, and here it will be lambda py. And now let me apply P inverse on the left hand side. So I'll get P inverse APY is equal to lambda, and P inverse P would be identity, so it will be simply Y. What it is yielding us? Let us say this is some matrix B. When it applies, this would be Y. When it applies to Y, it gives you lambda Y. Okay, it gives you same eigenvalue which you are getting on operation of A over X. So this particular matrix, let's say B, which is derived from P inverse AP, happens to be a diagonal matrix. Happens to be a diagonal matrix. So diagonal matrix, and further, this particular eigenvalue of B also is equals to eigenvalue of A, right? This transformation P inverse AP is called as a similarity transformation. This is called as your similarity transformation. This is called as your similarity transformation. So one has to remember what is a similarity transformation. By the help of a similarity transformation, we are able to diagonalize this matrix A in such a way that the eigenvalues of B and eigenvalues of A are the same. Okay. So in order to diagonalize a matrix, all we need to determine is what? We need to determine this matrix P. We need to determine this matrix P. And once we determine this matrix P, then we can always find this B, which is equals to P inverse AP, and which is a diagonal matrix. And all you know that in diagonal matrix, all the eigenvalues lie on the diagonal. All the eigenvalues are nothing but they are the diagonal entries. Okay. One should remember that if P inverse AP is a similarity transformation, so is your P inverse. That is also similarity transformation. That is also your similarity transformation. Now, okay, and once we connect both of these things, you're like, for example, if B is equals to what? P inverse AP, we say that B is similar to A, and similarly we can say that if A is what? A would be P B. A would be what? A would be P B P inverse. So here we would say that A is similar to B. Okay, so these are what you know as similar matrices. Now let us list some properties regarding. Let us list some properties of similar matrices. Let us list some properties of similar matrices. Property number one, it's quite easy to see that every matrix is similar to itself. Second, if A is similar to B, then it implies that B is similar to A. And if B is similar to A, then it implies A is similar to B. So you can say that reflexivity lies here. Third, if A is similar to B and B is similar to A, then you can say that A is similar to C. Okay. Now, one of the important properties is this. Always remember, if as we saw just a little bit before, that if the matrices are similar to each other, then both of them have the same eigenvalues. If both of them have the same eigenvalues, both of them will have the same characteristic polynomial as well. Okay, so I'll write it here that similar matrices have the same characteristic polynomial. Have the same characteristic polynomial. Have the same characteristic polynomial, and hence they have the same eigenvalues. In fact, eigenvalues not only distinct ones, even if they are repeated, then also eigenvalues will remain the same. All the more their multiplicities will also remain the same. So hence they have same eigenvalues. What should I write? Inclusive of multiplicities. So let's say if an eigenvalue of A is 2 and it is repeated like 2 times, then for B, if it is similar to A, the eigenvalue that is 2 in B will also be repeated 2 times. Is that clear? Okay, and see, what I wanted to suggest was this. So for example, let us say I'm saying that B is similar to A. Let's say B is similar to A. Then what does it imply? I can write that A is equal to, sorry, B is equal to P inverse AP. Or in other words, I can write that my B is equals to what? B is equal to, sorry, A is equals to what? Okay. So let's say this is your case. Okay. Now you see, or anyway you can write. You can write this as this also. Anyway, because I told you that if you write P a P inverse AP or a P inverse, this is one and the same thing. Okay, so whichever way it suits you, whichever way it suits you. Okay, now see, if I want to write the uh, B minus lambda I, what it would be? Let us write P inverse minus, I will write it as lambda into I will write P into P inverse. Okay, so this identity I'm going to write P inverse. So this is like uh, P inverse minus P, I'll write it here. Okay, and deliberately I'm going to write lambda into I, and here it is P inverse. I hope it is clear. Now if I write this way, I can take P common out and I'm getting A minus lambda I here, and then I have P inverse, right? If I take P common, I have this A minus lambda I and post multiplied with P inverse. So your B minus lambda I this. What would be determinant of B minus lambda I? That would give me the characteristic polynomial corresponding to B. This will give me what? This will give me characteristic polynomial. This will give me characteristic polynomial corresponding to B, right? And if this is the case, this will be like determinant of P times determinant of A minus lambda I, and this will be determinant of P inverse. And always remember this thing, determinant P inverse, this will be like determinant P inverse will be determinant of identity, and determinant identity is simply 1. So eventually what we've got that determinant of B minus lambda I is equals to determinant of A minus lambda I. So clearly you can see that both of them have the same characteristic polynomial. When both of them solve the same characteristic polynomial, therefore the eigenvalues are similar. Okay, and eigenvalues are similar and even of the same multiplicities. Please do remember that. Okay, now let us think about something else. Let's say this. Okay, now the please remember that it may so happen, or it may so happen that the matrices have same characteristic polynomial, but they do not have, but they are not similar. So the matrices have same characteristic polynomial, but they are not similar. Please remember, if they are similar, then they will have the same characteristic polynomial. It may so happen, let's say if you have a matrix, two different matrices, they may have the same characteristic polynomial, right? But they are not similar. But if the matrices are similar, then they will always have the same characteristic polynomial. Is that clear? Are you getting my point? That is what I want to say, that the converse of statement is not true. I hope everything is clear. Please let me know. Is that clear, I guess? Okay. So now let us move further and let us see a few more things regarding diagonalizability. Okay. Sure. So please think about this. So one of the thing is that we have told that the eigenvalues will be of the similar matrix will be same. But what about eigenvectors? So in general, note that I'm writing in general. eigenvectors eigenvectors of similar matrices eigenvector of similar matrices uh, are not the same are not the same. However, we can relate them. However, we can relate. So, what were the eigenvectors? If you remember, I gave you the equation Ax is equal to Py, Ax is equal to lambda x, and then I changed x is equal to Py. So, I can relate eigenvectors by this particular matrix, P. So I know that when I'm going to let's say see when I'm going to find the uh, when I'm going to diagonalize my A, I need to find this P, right? And once I find this P, then I will be able to diagonalize A. And what did I got? If you remember, I got this P inverse AP y was equals to lambda y. So it guaranteed me the similarity of the eigenvalue. So this was like B, and the B when operated on y gives you lambda y. So B also has the same eigenvalue as that of A, right? This is what we did earlier. Okay, this is what we did earlier, but it did not guarantee me what the similarity of eigenvectors. Since the eigenvector here is y, however, we know that the original eigenvector, which is of the original equation, that is Ax is equal to lambda x, this x can be related to Py, right? Is that clear? Now, in particular, in mathematics and even physics, now this if matrix P happens to be a unitary matrix, if this matrix P happens to be a unitary matrix, then the transformation, that is x is equal to Py, is called as a unitary transformation. If this matrix P happens to be a orthogonal matrix, then it is called as the orthogonal transformation. Then it is called as the orthogonal transformation. That is what I want to say. Let's say if this P exists and then we can diagonalize the matrix. Let's say I can diagonalize this matrix B is equal to P inverse AP. Okay, or similarly I can write A is equal to PBP inverse. Okay, so now if this P is unitary, that is if PP dagger is equal to identity, or P inverse is equals to P dagger, if this is the case, then I can write that this is my unitary transformation. Then I can write that this is my unitary transformation. If if this happens to be orthogonal, that is if P inverse is equals to P transpose, if P inverse is equal to P transpose, then I can say that this particular transformation is called as the orthogonal transformation. This is called as the orthogonal transformation. Then this is called as the orthogonal transformation. Now let us do a few questions and then we will go ahead. So now I'm giving you a question, a simple one, and then we'll see if you are well to do with that. Then we'll move ahead. Okay. So the question says that there are two matrices that I'm giving to you, and these are 2 cross 2. So it will be easy to find. I'm giving you a question. Take some time and try to do it. Let us say that A is equals to what? It is equals to 1, minus 3, 2 and 0. Your B is equals to 0, 2, minus 3 and 1. Okay, and I'm giving you, let's say I'm giving you this P. I'm giving you right now P, which is equal to P inverse is equals to 0, 1, 1, 0. I'm giving you this P. Try to find that A is similar to B. This is something that I'm going to do. It's easy. Try to do it. So in order to find that A is similar to B, you have to use the similarity transformation. You have to use the similarity transformation. So what I have to do, see, simple. I have been given A, so I have been given A. I have been given P also because I have given it for your convenience so that you don't waste much of your time finding P answer. So what I have to do, I have to find P inverse AP. So what is P inverse? This is 0, 1, 1, 0. Acha, okay. How to find? I'll write it later on. But here you have this 1, minus 3, 2, and 0, and then again this is 0, 1, 1, 0. Okay, so it would be equals to what? So it would be equals to writing 0, 1, 1, 0. Here you have this minus of 3, then you have 1, then you have 0, and then you have 2. And now apply this. What you will get? You will get 0. You will, I think you will get 2 here. You will get a minus 3 here, and you will get a 1 here. So what it is equal to? Is it not equal to B? See, it is equal to B. So clearly A is related to B using similarity transformation. Therefore, I can say that A is similar to B. Okay. Now, in general, whenever you are supposed to find the inverse of a 2 cross 2 matrix, then you don't have to do lot of things. I'm just writing a short way of doing it so that you remember for your exam also. It is like well established, so don't worry. It is not even a short trick, but just that don't waste your time. So basically, if I have to do this, then A inverse would be simply 1 upon determinant. So the determinant would be what? AD minus of BC. This is determinant. And adjoint, don't waste time, just replace these two. So just do this D and A here. And then what you can do, just take a minus of on this side. So this will be minus B and minus A. And this is how you write your, what you can say, this is how you write your, this is how you write your inverse. This is how you write your inverse. Okay. I hope it is clear. Inverse for 2 cross 2. This is how you write inverse for 2 cross 2. Just do this thing. This is your nothing but this is adjoint of A. And this is nothing but this is determinant of A. This is determinant of A. This is adjoint of A. Isn't it? So, okay. Now, let us go a little bit further and try to do a few more questions. See, when it comes to exam, nobody is going to ask you that long question, but at least you should be able to do a few of them, and then we'll see. Okay, now what is the condition? So what is the condition? What is the thing? What we are doing by this particular transformation? One thing is very much clear, that one thing is similarity transformation that we are doing. One thing is very much clear, that we are doing the similarity transformation. Now, by similarity transformation, what we in starting I told you that I can reduce my matrix A into a diagonal matrix. I can reduce my matrix A into a diagonal matrix, right? And if the matrix is diagonal, if the matrix is diagonal, and it's then the diagonal elements will be nothing but they will be the eigenvalues of lambda. These diagonal elements will be nothing but these elements would be diagonal elements of diagonal elements will be nothing but it would be equals to eigenvalue of A. Is that clear? I hope it is clear. Okay, now see, if I have to diagonalize my matrix, the first thing is we have to make a P matrix. We have to make the P matrix. So I'm writing a little bit of algorithm for you that you can follow. and then we will do the questions. So how to diagonalize a matrix? So diagonalization of a matrix A of n cross n. So let us say that this particular matrix A has n distinct eigenvalues, has n distinct eigenvalues lambda I. Let us say this A has n distinct eigenvalues lambda I, corresponding to which we have n linearly independent eigenvectors. Corresponding to which we have n linearly independent eigenvectors. Let us say xi's. So that what does it imply? It implies that A xi would be equals to lambda I xi. Now what I'll do, how to construct this particular matrix P. So I'm giving you a suggestion, or and this is quite established algorithm, how to find this P. So what is P? P is nothing but P is a matrix whose columns are P is a matrix whose columns are nothing but the eigenvectors xi's. Eigenvectors xi's. Okay, and once this P is found, then I can always find P inverse AP in order to diagonalize my matrix A. So it diagonalizes your matrix A. And what is meant by diagonalization? It is meant by diagonalization that your matrix A uh, gets reduced to a diagonal matrix. Gets reduced to a diagonal matrix. I hope it is clear. Okay, so now let us diagonalize a simple matrix so that you're able to understand this thing, and then I'll leave it for you to do more questions on diagonalizability. I'll focus more on the qualitative part of diagonalizability today. Okay, so the question is, try to diagonalize this matrix A given by minus of 17, 30, minus of 10, and then you have this 18. This is your A, and you want to diagonalize this A. So the first thing that you need to find is the eigenvalues. First thing that you need to find is the eigenvalues. So let me find A minus lambda I equal to 0. This would give me lambda minus 18. This will be t minus lambda. And then there would be lambda plus 17 here, and then minus minus plus 300 is equal to 0. So what you will get? You will get lambda square. Then you will get a I think minus of lambda, and then 18 into 17, what it would be? Just let me calculate. 18 into 17. 18 into 17 is 306. So you're getting minus 306 plus 300, so you'll get minus of 6 equal to 0. So what it is giving me? It is giving lambda square minus 3 lambda plus lambda minus 6 plus 2 lambda. So this is it. So one of the eigenvalues I'm getting minus 2, another eigenvalue I'm getting 3. So two eigenvalues I've got. Corresponding to it, we have to find the eigenvectors. So I have to find eigenvector corresponding to lambda 1, and corresponding to lambda 2 also I have to find an eigenvector. And once I know the eigenvector, then I can construct the matrix P. So corresponding to x, this one, I have the eigenvector, let's say x1, and what it would be. So let me try to do it. So it is minus 2. So A minus lambda I. So you will have this A minus lambda I x1 is equal to 0. So this would be like minus 15 here, and minus minus, I think uh, plus 20 here, I guess. Okay, here it would be 30, here it would be minus 10. Okay, sorry, it is like x 1 and x2. So what you're getting equals to uh, x1, if it's so it implies that my eigenvector x1 I can write 2 1, I can write 2 1, right? So this is 2, this is 1. Similarly, if I want to find the eigenvector corresponding to lambda 2, so that is, let's say this is x2, and if I use this thing, so I'm getting minus 20 here, I'm getting 30 here, here I'm getting minus 18, and here I'm getting minus 18, minus 10, not minus 10 even, minus 18 only, right? And minus 3, so it will be like, see, minus 3 is minus 20, and 18 minus 3, so this is minus 10, no, sorry, this is minus 10, and this would be 15, and then you have this x1, and then you have this x2. So clearly you can see that your 20x1 is equals to 30x2, and if this is the case, then you can always write this as 3, this as 2, so your x2 would be similar, it will be 3 2. So you've got your matrix P, which is nothing, which is equals to what? It is equals to 2 1 3 2. I told you that try to make the column vectors as the from the column vectors, try to make the eigenvectors as the column vectors of matrix P. Now what would be P inverse? I told you, for P inverse, all you need to do is just take a negative on this side and just swap these two. So these are 2, so this will be like same, and here you will have minus 3 and here you will have minus 1. So this is how you can write your P inverse. Now let us try to find P inverse AP. This is what it was written, right? P inverse AP. What it would be? So I know that my A is, so this is 2, this is minus 3, this is minus 1, this is 2, and this is minus 17, this is 30, this is minus of 10, minus 18, 2, 3, and 1 and 2. Okay, now let us try to find what it would be. So it would be equivalent to writing 2, minus 3 here, minus 1, 2 here, and what it would be, see, I think first would be minus 4, 51, 60, 69, so this will be 9, so this will be minus 2 here, so this will be, I think, 6 here. Okay, and if I do another calculation over it, so what I'll get, 2 minus 8 and minus 8 plus 6, so this will give me minus 2 here, 18 plus 18 0, so plus 4 0, and the last one would be 3. So clearly this reduces to a diagonal matrix. This reduces to a diagonal matrix with what? In diagonal matrix, what happens? The eigenvalues lie on the diagonal side. So eigenvalues lie on the diagonal side. So if the eigenvalues are lying on the diagonal side, you can see this P inverse AP is nothing but minus 2 0 0 and 3. Is that clear? I hope it is clear. Please let me know if there is an error or issue that you're not getting. Okay, so this is how you diagonalize a matrix. Okay, what all are necessary things for diagonalizing a matrix? For your own homework, try to do them from your textbooks. And once you do those questions, you have to do a good amount of questions. But overall, you should be, in physics, you should be able to understand what are the conditions for diagonalizability. And one of the most important matrices that we use is called as a Hermitian matrix. So always remember, a Hermitian matrix can be diagonalized using a unitary matrix, or using a unitary transformation. Always remember. So for what I'm saying, I'm not writing the proof for it because it will be a very rigorous kind of proof, but overall understand that for a Hermitian matrix, you would need a unitary matrix in order to diagonalize this. So this is something that is very important. And Similar to Hermitian, what we had the real counterpart for this, a real symmetric matrix. So a real symmetric matrix, a real symmetric matrix can be diagonalized, can be diagonalized by a real but orthogonal matrix. So instead of unitary, you have orthogonal matrix here. This is something that I'm writing without proof. Please remember this. I hope it is clear till now. Please let me know if there is any issue. I'm waiting for a minute. If there is an issue, please let me know. Okay, I hope it is clear till now. Please let me know. Okay, so I guess it must be clear. Let us go a little bit further. Okay, now let us try to diagonalize a matrix and understand it. So let us try to diagonalize a matrix, a Hermitian matrix. So let us take an example. Let us take an example of Hermitian matrix. Let us take an example of Hermitian matrix. Okay, and the example is let us say A is equals to 2, 3 minus 3 iota, and then it is 3 plus 3 iota here, and here it is 5. And it's quite easy to see that this is a Hermitian matrix. See, clearly you can see that A dagger is equals to A. A dagger is equals to A. Okay. Okay. So I told you that a Hermitian matrix is diagonalized using a unitary transformation. That is, the matrix that is responsible for the diagonalization of the Hermitian matrix, that matrix P, is a unitary matrix. And most often you will find that I would be taking example of 2 cross 2. Okay, 3 cross 3 I will be leaving for you as a homework. Try to do them. If you have a problem with certain problem, kindly refer it to me. I'll see. See, the eigenvalues. The first thing that you need to find is the eigenvalue. So a minus lambda I modulus is equal to 0. So if this is the case, then I'll get 2 minus lambda, I'll get 5 minus lambda, and here I know this is simply minus of 3 square plus 3 square, this is minus of 18, I guess. Sorry, minus 18 only, because this is 3 square and then plus 3 square. So minus of 18 equals to 0. So what you will get lambda square, and then this is minus of 7 lambda plus 10 minus 18, this is minus of 8 equal to 0. So you are either getting lambda is equal to 8, or you are getting lambda is equal to minus 1. So there are two eigenvalues to it. Lambda 1 would be 8 and lambda 2 would be minus 1. Now if corresponding to these, both of them, like lambda 1 is equal to 8 and lambda 2 is equal to minus 1, you can find eigenvectors. So what would be eigenvectors? Let us see. So let us say x1 is the eigenvector corresponding to this. So what I will get, it would be minus of 6 here, it would be minus of 3 here, it would be 3 minus 3 iota here, and it would be 3 plus 3 iota here. And then you can write it as x1, and here you can write x2 equal to 0. And what are you going to get? You're going to get that 6x1 is equals to, what should I write? 6x1 is equals to 3 minus 3 iota x2. Okay, 6x1 is equals to 3 minus 3 iota x2. Or other equation also, the same thing will happen. I can write it as 3 plus 3 iota x1 is equals to 3x2. So if you actually divide this by 3 plus 3 iota, so and then take a, what you can say, so if you divide it, so let's say x1 is equal to what? X1 is equal to 3 upon 3 plus 3 iota x2, right? And let us say I do this 3 and multiply by above and below by the conjugate, so it will give me 18 here, and here I'll get 3 minus 3 iota x2, so I'll get 6. I'll get a 6x1 is equal to 3 minus 3 iota x2. In any case, I'm going to get the same result. So what would be my x1? X1 would be simply, if I take x2 as 1, if I take x2 as 1, then x1 would be 3 minus 3 iota upon 6, which is equal to 1 minus iota upon 2, which is equals to 1 minus iota upon 2. Is that clear or not clear? I guess it is clear. Okay, so okay, so now see, okay, so this is, I think it's better if I take this as 1. Let me take this as 1. If I take this as 1, um, if I take x1 as 1, what I'll get? If I take x1 as 1, I will get that x2 is equal to 6 upon 3 minus 3 iota. Okay, so if I take this as 1 instead, I'm just taking it for, you can take this also. Uh, just for the convenience, I'm taking, I want that somehow it gets a cancellation. So, okay, that would also do. So this will be like 3 plus 3 iota divided by, I did it 18 here and there was a 6 here, so this cancel, this will give me 3. So it will be simply 1 plus iota. So life will become easy for me here. So it is 1 plus iota here, right? Okay, and let us try to normalize it also. In order to normalize it, I have to divide it by root over 1 square plus mod of 1 plus iota ka square. Please remember this is mod. So root over 1 plus what it is, 1 plus iota mod is root 2, and root 2 square is 2. So this will be like, if I have to normalize it, then the the eigenvector corresponding to lambda is equal to 8 will be 1 upon root over 3 and 1 and 1 plus iota. If it's, I hope it is clear. And corresponding to another eigenvalue, which was, I think, just let me see, another eigenvalue was minus of 1. So another eigenvalue was minus of 1. So if I use minus of 1, so what I'll get uh, uh, this would be 3, this would be 6, this would be 3 minus 3 iota, this would be 3 plus 3 iota, and here you have this, let's say x1 x2 equal to 0. And what you will get from here, you will get from here 3x1 is equals to 3 iota minus 3 x2, right? Or I can write that my x1 is equals to iota minus 1 x2. Okay, so if I use x1 as 1, x2 as 1, sorry, if I use x2 as 1, I will get the another eigenvector also. So another eigenvector x2 would be simply what? Uh, Again 1 over root 3, because this mod is also 1 over root 3. Let's say x2 is 1 and this will be iota minus 1. So in totality, I have found a matrix U whose dagger I'll let you know, so that you are able to verify that for Hermitian matrix I'm deliberately writing it as U, because I taught you that for Hermitian matrix the transformation matrix, that is P, which actually transforms a Hermitian matrix to a diagonal matrix, happens to be unitary matrix. So always remember, a Hermitian matrix can be diagonalized using unitary transformation. Okay, and let me write 1 over root 2 common outside, and so this will be the first one, would be iota minus 1, and then this is 1, and whichever way it suits you, it's not that you have to write it here, one and the same thing. Okay, clearly you can see that if I take a dagger, what I will get, I'll get 1 over root 2, this will become iota, this will become what, so this will become uh, minus iota minus 1 1, and this will become 1 and 1 minus iota. This will be u dagger. Now try to write u dagger and u. Try to write u dagger and u. It will be equals to 1 upon 3, and this is iota minus 1 1 1 1 minus iota. Here it is iota minus 1 1 1 1 plus iota. And try to do this. This is 1 over 3, and here you will get what? Here you will get iota minus 1 whole square plus 1. Then here it is iota minus 1 plus 1 plus iota. Then here it is iota minus 1 plus 1 minus iota, and here it is 1 plus 1 minus iota square. I hope it is clear. Okay, so what you are getting after all, this is 1 upon 3. 1 minus iota whole square will give you iota square. Okay, it is not 1 minus iota square, right? Okay, it is 1 minus iota whole square, right? So I don't know why I'm not getting it. So u dagger u dagger is 1 upon root 3 minus 1 minus iota, that is absolutely fine. 1 1 1 minus iota, okay. And here you have what? Okay, this is something I've written wrong now. So this is u dagger is minus 1, so it is not 1 minus iota. Okay, sorry. So here I'm writing it, so it would be equals to, if I take a minus common, then it will be equals to 1 plus iota into 1 minus iota plus 1. So 1 minus 1 plus iota 1 minus iota will be 1 minus iota ka square, which is 2, plus 1, so this will be 3 here. This will also get cancelled, sorry. So this will give you minus iota minus 1 plus 1 plus iota. So you would simply get a 0 from here, and I think this was fine. I think this was fine. So here you are getting, so you are getting 0 here, and here it is 1 1, and iota square is minus 1, and this is 3. What you are getting 1 0 0 1. Clearly this matrix U is a unitary matrix. This is what I taught you, that for a Hermitian matrix the similarity transformation can be brought about by the help of unitary transformation. Now let us try to find the let us try to diagonalize my matrix A. Let us try to diagonalize my matrix A. So U inverse A U, right? And in fact, you know, for a unitary matrix U dagger, U is equals to identity. So whatever you found U dagger, it is nothing but it is equals to U inverse only. So U dagger, what we found it as minus iota minus 1, and I had 1 here, I had I think 1 here, and then I had 1 minus iota here. So whether you write U dagger or whether you write U inverse, this is one and the same thing. Here you had root over 3. What would be A then? What would be A then? Okay, what would be A? So A is that I think that matrix, originally matrix was I think 2, and here it was 3 minus 3 iota, and here we had 3 plus 3 iota, and here we had 5, and again 1 over root 3. So I'll get 1 over root 3. I'm writing it here, and here it was iota minus 1, 1, and it was 1 and 1 plus iota. This is how it was. Now try to find. So it will give me 1 over 3 is initially I'll get a 1 over 3, and this is minus iota minus 1, 1, 1, 1 minus iota. And here what you're getting 2 iota minus 2 plus 3 minus 3 iota. Then this is 2 plus 3, 1 minus iota into 1 plus iota. Then this is 3, 1 plus iota into iota minus 1 plus 5. And then you have this 3 plus 3 iota plus 5 plus 5 iota. So eventually what I'm getting 1 upon 3 here. This is minus iota minus 1, 1, 1, 1 minus iota here. And what it would be, see, this is equals to 2 minus 3 iota is minus iota. What is minus 2 plus 3? This would be plus 1. This is 2 plus 3, and this is 1 minus iota into 1 plus iota. It would be 1 minus iota square, and 1 minus iota square is simply 1 minus iota square is simply 2. So this will be 6. 6 plus 2 would be 8. So I'm writing directly 8 here. And 3 into this. So I'm writing this would be like, I hope it is not wrong, otherwise we'll not be able to figure out. Let us check it once more. So 3 times 1 plus iota into iota minus 1 plus 5. Okay, so this is fine. So it will be like iota square minus of 1, which is minus 2, into 3 is minus 6, 5 minus 6 is minus 1. And here you will get, I think, 8 plus 8 iota. This is quite easy to see. Okay, now let us try to find complete solution. This would be 1 plus 3. What it would be equals to? It would be equals to iota minus 1 into iota plus 1. And this would be minus 1. Then again minus 8 iota minus 8 plus 8 plus 8 iota. This I'll get minus iota plus 1 minus 1 plus iota. So this is all we are getting 0 only here. And this is 8 plus 8. Okay, 8 plus 1 minus iota. Sorry, 8 plus 8, 1 plus iota into 1 minus iota, right? This is how you are getting it. And eventually I'm getting 1 upon 3, 1 minus iota, and this would be minus of 2, and minus of 2 minus of this is fine. I think there's a mistake here. Iota plus 1 minus of 2. There is some mistake somewhere, I don't know. Okay, let me check. So this will be minus 2, I think. This will be minus 2, okay. Minus 2 minus 1, this would be 0, this would be 0, and what it would be? I think it would be this would be 2, so it will be 24, I guess. Okay, so it implies we are getting minus 1, 0, 0, and 8. This is what is your matrix. And I know that I know that the eigenvalues for A were nothing but they were, I think, minus 1, 8 only, right? Minus 1 and 8. I think 8 it was, right? Yes. So clearly, by the help of a unitary transformation, we are able to diagonalize the Hermitian matrix given to us. Okay. So I hope this makes my point clear that for a Hermitian matrix, okay, for a Hermitian matrix, always remember you need a unitary transformation in order to diagonalize the matrix. I hope it is clear now. Okay, so I'm not going to see this much amount of time it has taken for me to take or do a diagonalization of a 2 cross 2 matrix. So I hope you will do 3 cross 3 on your own. Now let us discuss some very qualitative parts regarding your diagonalization, and then we'll do some questions that have come in the examination so that you would understand what is the level of the examination. Okay, what do you mean? Some qualitative points regarding some qualitative points regarding diagonalizability of matrices. So if I want to state a few points without proof, I'm writing. First thing, the question arises that till now we've understood diagonalization. Now we want to actually understand as to what are the conditions which are required to make a matrix diagonal. Okay, that can we make every matrix diagonalizable? Okay, so this is a question that always arises. Okay, so the prime question is that why we are doing it. So is it possible? Is it possible to know whether a matrix A can be diagonalized or not? Is it possible to know whether matrix A can be diagonalized or not? So there are few points that I'm writing without proof. Okay, without proof I'm writing. The first thing is an n cross n matrix. An n cross n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So if a matrix A is such that it has n linearly independent eigenvectors, then A is a diagonalizable matrix. Okay. So if you remember that when we were doing Hermitian matrices, what we did, so for Hermitian matrices, we found that the eigenvalues, whether they are distinct or whether they are not distinct, whether if they are distinct, then we can always find a set of n linearly independent orthogonal eigenvectors. If you remember, this is something that we have done in the eigenvalues. Okay, and if even if there are some eigenvalues with R multiplicity, these will generate R linearly independent orthogonal eigenvectors. Plus, then there would be some n minus R other eigenvalues which are distinct. So in totality, for Hermitian matrices, always remember whether whether it has distinct eigenvalues or whether it does not have a distinct eigenvalues. So if it does not have a distinct eigenvalues, and let's say one of the eigenvalue is repeated R times, so corresponding to that eigenvalue, you have R linearly independent eigenvectors, and remaining n minus R eigenvalues you will have n minus R eigenvectors. In totality, whether your matrix Hermitian matrix contains all the eigenvalues as distinct ones or some distinct and some same, in totality we can say that Hermitian matrix will always have the eigenvectors of Hermitian matrix will always form an orthonormal set of uh, n linearly independent eigenvectors. So always remember a Hermitian matrix is diagonalizable, and it is diagonalizable using, I have told you just a minute before. So every Hermitian matrix can be diagonalized a using a it can be diagonalized using a unitary transformation. Using a unitary transformation. It can always be diagonalized using a unitary transformation. I hope it is clear now. Now you see this is one. Another thing is that n cross n matrix, if an n cross n matrix has n distinct eigenvalues, it has n distinct eigenvalues, then also the matrix A is diagonalizable. Let's say A I'm writing. If an n cross n matrix A has n distinct eigenvalues, then also it is diagonalizable. As I told you about Hermitian matrix, a symmetric matrix is a special case for Hermitian matrix. Always remember, every real symmetric matrix A, every real symmetric matrix A is diagonalizable, is diagonalizable, and in particular using orthogonal transformation, using orthogonal transformation. Just remember these points, okay? Using orthogonal transformation. Now, the biggest thing, see, if I told you that if a matrix of order n is diagonalizable, then I told you that it will have either n set of linearly independent eigenvectors or it has n distinct eigenvalues. Okay, so a very important statement, a matrix A, I guess it's this is 5. Okay, so a matrix A is diagonalizable if its minimal polynomial, not characteristic polynomial, minimal polynomial, if and only if its minimal polynomial if and only if its minimal polynomial has distinct roots, and by which I mean that if I have to write my minimal polynomial, then I can represent it in terms of linear power of linear factors. So if I can write my minimal polynomial in terms of linear factors, n linear factors, like as a product of n linear factors, then I can say that my matrix A is diagonalizable. My matrix A is diagonalizable. Is that clear? Is that clear or not clear? Please let me know, and then we'll move to few other things. Okay, so let us move a little bit further. Now let us try to test our results onto a few questions, and then we'll do a few random questions as well. Okay. Okay. So the question is uh, whether this matrix is diagonalizable. So now just don't diagonalize it. Just think about diagonalizability. So I want to determine that following matrices are diagonalizable. So following matrices are diagonalizable or not, let us try to find this. Question number 1. The matrix is A 3 1 minus 1 2 2 minus 1, then you have this 2 2 and 0. What do you think, this matrix is diagonalizable or not? What do you think this matrix is diagonalizable or not? So in order to find that, let us first find the number of eigenvalues. The first test is, let us first find the number of eigenvalues. So eigenvalues would be, I think, 3 minus lambda. Here it is 1, here it is 1, here it would be 2, here it will be 2 minus lambda, here it will be minus 1, here it would be 2, here it will be 2, here it would be minus lambda. And if I want to find this as equal to 0, what I will get? I will get 3, I'm writing 3 minus lambda, and this is minus 2 lambda plus lambda square, minus plus. So this would be plus here, minus 1, this will be, okay, and then minus 1, 4 minus of 2 minus 2 lambda equal to 0. Okay, so this is 1, and what I'm getting, 3 minus lambda here. Here I'm getting lambda square minus 2 lambda plus 2. This would be 0, see clearly. This will not be 0, sorry. And this is 1 now, sorry. This would not be 0. Okay, so sorry. This would be minus 2 lambda here, and then I think it is plus 2 here, sorry. So this will be like 2 lambda minus of 2, and this will be minus, this would get cancelled, 4 minus 4 would get cancelled, this is minus 1, two lambda, right? Minus 2 into minus 2 lambda. So this is, I think, 2 lambda. I think this is fine, is equal to 0. Okay, so this is one thing. Now you see this 2 lambda gets cancelled here. Eventually, what are we left with? So I think we are left with 3 lambda square minus 6 lambda plus 6 minus lambda cube plus 2 lambda square minus 2 lambda minus 2 equal to 0, right? So we are left with, if I take a minus lambda cube here plus 2 lambda square plus 3 lambda square, this is plus 5 lambda square here, okay, minus 8 lambda and plus 4 equal to 0. Or in other words, I can write lambda cube minus 5 lambda square plus 8 lambda minus 4 equal to 0, right? Okay, and if I use lambda is equal to 1 here, if I use lambda is equal to 1, I know one of the roots is simply lambda is equal to 1. So I'll use lambda minus 1, and I'll try to take up this thing. So this is lambda cube minus 5 lambda square plus 8 lambda minus 4. So let us say this is lambda square, you will get a lambda cube here, minus lambda square plus, so it will be minus 4 lambda square, so you'll get minus 4 lambda, so it is like minus 4 lambda square, and this minus 4 lambda, so you'll get 4 lambda minus 4, so you are getting, I think, minus 4. So basically the equation is lambda minus 1 into lambda minus 2 whole square equal to 0. Okay, is that clear? So this is your characteristic equation. This is your characteristic equation. This is your characteristic equation. Now I know that for every matrix A satisfies its characteristic equation. So every matrix A satisfies its characteristic equation. And let us say I am discussing about n cross n, then the characteristic equation is always, you know, of order n, of degree n. I told you that if a polynomial exists, which gets annihilated by which gets annihilated by, annihilated means if I place my matrix A into that polynomial, it becomes 0. So if it gets annihilated uh, by matrix, let's say A, whose characteristic polynomial I'm finding, and if a matrix A is there which can annihilate another polynomial of degree less than n, then this particular polynomial is called as a minimal polynomial. I hope I have taught you before what is a minimal polynomial. So what is a minimal polynomial? So in general, I know that if I have to write the characteristic polynomial is this. And if I say that, okay, there exists a polynomial of lesser degree than this particular characteristic polynomial, which also satisfies my matrix, then this is called as your this is called as your minimal polynomial. And what I taught you this morning, that if a minimal polynomial has independent n has n factors, that is, if your eigenvalues can be factorized in terms of linear factors, and minimal polynomial is such that you can factorize it in terms of linear factors, then the matrix is diagonalizable. Now let us consider this. What was your characteristic polynomial? So for your instead of, I can write a minus I into a minus of 2i. This was 2i whole square. This was your characteristic polynomial, right? This was your characteristic polynomial. This was your characteristic polynomial, right? Is that clear? Now, what did the statement said? Statement said that the minimal polynomial, okay, and it was if and only if condition, if you remember. So a matrix is diagonalizable. A matrix is diagonalizable if the minimal polynomial has distinct eigenvalues, or you can say that your minimal polynomial can be represented as lambda minus lambda 1, lambda minus lambda 2 dash dash dash, lambda minus lambda m, let's say, if your distinct minimal polynomial is of degree m. If this is what you can do, then I would say that my and this is if and only condition. That is, if I find a minimal polynomial, which does not have distinct eigenvalues, if I find a minimal polynomial which does not have distinct eigenvalues, then what will happen? Then it will so happen that what you can say, then it will so happen that the matrix is not diagonalizable. What I am trying to convey you, let's say this is your characteristic polynomial, this is of cubic. If I want to find a quadratic polynomial which annihilates a, okay, then that will be the minimal polynomial. See, characteristic equation degree is 3. If I find a polynomial of degree 2 which annihilates my matrix A, then this particular polynomial would be called what? It would be called as your minimal polynomial, right? It will be called your minimal polynomial. But if it is not the case, that you cannot find a quadratic one which satisfies your matrix, then it implies that your minimal polynomial is nothing but then it is equals to your characteristic polynomial only. Yes or no? Please let me know here, yes or no. Okay, is that okay? So what I'm trying to say, देखो, minimal polynomial will be arising. See, characteristic polynomial will be of degree 3. If I get a polynomial of degree 2 which annihilates my matrix A, then this polynomial of degree 2, that is this quadratic polynomial, will be called as a minimal polynomial. because it is satisfying my A and its degree is less than 3. But if it so happens that you cannot find a minimal polynomial of degree 2, then obviously this minimal polynomial is nothing but it is the characteristic polynomial itself, right? So what I would do is try, see, there are only one possibility. There are, see, if I have to make a minimal polynomial of degree 2 from here, what I can do this, a minus lambda I, and instead of 2 I just write a minus 2I, and let us try to see that whether it satisfies or not. So whether it satisfies it or not, because there is no other way of making, see, it is power 2, so it will give me 3 order 3. But if I reduce this 2, or I can judge a minus 2I whole square. These are the two possibilities that I can think upon. Okay, these are the two possibilities that I can think upon. Now you see, if you find a minus I, what was a? I think I'm writing a all over again so that you don't get confused. It was 3 1 minus 1, and then it was 2 2 minus 1. It was 2 2 0. Now let us try to find a minus I. So what would be a minus I? And if I want to find 2 minus 2, sorry, a minus 2I, it would be 1 1 minus 1, because this is 2 0, and this would be minus 1, this would be 2 2 minus 2. And if I multiply this, what I'm getting, if 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 this is a minimal polynomial, let's say I'm considering, let's say this is your minimal polynomial, then what should I get? I should get a null matrix here, right? I should get a null matrix. And if I'm not getting a null matrix, then this is not a minimal polynomial. This is what it means. What is a minimal polynomial? A minimal polynomial is a polynomial which is of degree less than the characteristic polynomial which annihilates our matrix, or our matrix satisfies that particular polynomial, right? So let us find whether this is what I'll get. This would be 2, it would be 0, it would be minus 1. Okay. Here you will get, I think, 2, here we get 0. So, here you will get, I think, minus 1. Here you get 4, 0. Okay, minus 2. Clearly this is not a null matrix. Clearly it is not a null matrix. So therefore this is not the minimal polynomial. Other way you can think of is, you can try this. Try to find the square of this. Try to find the square of this. Try to find the square of this. I think I'm leaving it to you as a homework. Try to find this. This will also not come as a null matrix. It implies what? It implies that the minimal polynomial would be your characteristic polynomial. And see what I told you. If the minimal polynomial is 1, which can be written in terms of a linear factors, then only the matrix is diagonalizable. This is what is the last statement. Please remember. And I told you it is a star marker. So a matrix A is diagonalizable if and only if. If and only if means what? If the matrix does not have, if the minimal polynomial cannot be expressed in terms of linear factors, then it is not diagonalizable. Okay, so if the minimal polynomial has distinct roots, only then you can have this matrix, only then the matrix can be diagonalizable. But here what you see, that the minimal polynomial has double roots, has a double root at lambda is equals to 2. Clearly the minimal polynomial has a repeated root. Clearly it cannot be expressed in terms of linear factors of the eigenvalues. It implies that matrix A is a non-diagonalizable matrix. Hence, I can write that matrix A is a non-diagonalizable matrix. I hope it is clear. Okay. I hope it is clear. Okay, if you're not very comfortable with this, let's see the response. Okay, is that fine? Okay. Now you see, okay. Now, if at all you are not very convenient with this, then I also told you that it so happens, if it so happens that your matrix A has n linearly independent eigenvectors, this was I think the first thing that I wrote. If the matrix A has n linearly independent eigenvectors, then it is diagonalizable, otherwise not. Okay, so it is also if and only statement. So let us try to find the eigenvectors corresponding to this matrix, so that at least it becomes a comprehensive sort of discussion. Okay, and today we will only discuss this only. We'll do a quite amount of questions tomorrow, but please make sure that these are very important things. Okay, these are very important things for your exam also, and otherwise also. Eigenvectors corresponding to A. Eigenvectors corresponding to A. So if I want to find the eigenvector corresponding to lambda is equal to 1 at first. So if this is the lambda is equal to 1, what I would get? It is A minus I times the matrix X is equal to 0, right? And what I will get from here? I will simply get 2, 1, minus 1, 2, 1, minus 1. This is something that we've already evaluated. So I'm directly writing it 2, 1, minus 1. And then this was x1, x2, x3. Okay, just see this. This is something that we have already done, A minus I. Okay, so this is something that we have already done, so I'm writing this only. So from here I know what I'm getting. I'm getting 2 x1, and all these are redundant, all these are uh, uh, these two are redundant, so 2 x1 plus x2 minus x3 equal to 0. Another one is 2 x1 plus 2 x2 minus x3 is equal to 0. So if I subtract it, what I will get? I will get that x2 is 0. If x2 is 0, then you can take x3 as simply 1, and if you take x3 simply as x1 simply as 1, then x3 would be 2. So I can write it as 2, I can write it as 1 0 2. So this is the eigenvector corresponding to lambda is equal to 1. What about lambda is equal to 2? So for lambda is equal to 2, just remember I have already calculated this A minus 2i, so I'm going to directly use it here. So A minus 2i x is equal to 0. What it will yield me? It will yield me 1, 1, minus 1, 2, 0, minus 1, 2, 2, minus 2. And see, these are the same things. 1 and this is the same. And I'm here getting x1, x2, x3 equal to 0. And from here, if I want to find what I will get, from here I'll get 2x1 is equals to x3. This is one thing that I'm getting. And another thing that I'm getting is x1 minus x2 plus x3 equal to 0. And if 2x1 is equal to x3, if 2x1 is equals to x3, then I can also write, that 3x1 is equals to, no, if 2x1 is equal to x3, 2x1 is equals to x3, right? Okay, so if 2x1 is equal to x3, this is what I have written here, then minus x1, 2x1, right? 2x1, 2x1. If I write 2 here, so this will give me x3. So another one would be, if I use this equation, okay, if I use this equation, okay, so whatsoever, so if I use this x3 is equals to 2x1 here, right? Okay, okay, so we are getting only one, right? So if I use x3 is equal to 2x1, so I'll get 2x1, so I'll get 3x1 minus x2 is equal to 0. That implies x2 would be equal to what? It would be equal to 3x1, right? So in totality I can write that, my linear eigenvector would be, if x2 is 1, then sorry, if x1 is 1, then x2 would be 3, and if x2 is 3, and if x1 is 1, then x3 would be 2. So this is one of the eigenvectors. So clearly remember that for lambda is equal to 2, I have only one eigenvector, because the other equation that will be formed is actually linearly dependent on this. So basically this and this part will yield you the same equation. So originally you have only two equations, this equation number 1 and another equation from here. Are you getting my point? So only one independent, you can say eigenvector is here. So in totality, this particular equation has this particular, sorry, matrix A has two linearly independent eigenvectors. There are only two linearly independent eigenvectors. There are only two linearly independent eigenvectors. Since there are only two linearly independent eigenvectors, I can say that matrix A is non-diagonalizable, because I told you a matrix A is diagonalizable if and only if. So for example, the matrix is of order n, then it is diagonalizable if and only if it has n linearly independent eigenvectors. And here you can clearly see the matrix A is of order 3, and total number of linearly independent eigenvectors that I'm getting are only 2. I hope it is clear. Please let me know if that's clear, then I'll move further. Okay, is that fine? Now let us try to apply this particular concept into some different other matrices, so that you are well accomplished for your exam. Okay, let us see that which of the following matrices are diagonalizable. Which of the following matrices are diagonalizable? So I've already done one matrix, second matrix B. Let us say this is my matrix 2, minus 3, 0 and 0. Whether it is diagonalizable or not. Whether it is diagonalizable or not. So I know that this particular matrix, if I want to find, it will be 2 minus lambda ka square. 2 minus lambda into minus lambda is equal to 0. So it has lambda is equal to 0 and it has lambda is equal to 2. Clearly there are two distinct eigenvalues. There are clearly two distinct eigenvalues. If there are two distinct eigenvalues, then the matrix is diagonalizable. So let's say this is your matrix B, then B is diagonalizable. Indeed diagonalizable, no issues. Okay. Now think about this matrix, whether this is diagonalizable or not. 0, 0, 1, 0, 0, 1, and then you have 1, 1, 0. What do you think, whether this matrix is diagonalizable or not? This matrix is also diagonalizable. Just see, just think about it. If you do C transpose, what you are getting? You are getting 0, 0, 1, 0, 0, 1, and 1, 1, 0. What you are getting? This is it. So you can clearly see that your C transpose is equal to C. It implies what? It implies C is a real symmetric matrix. C is a real symmetric matrix. And I told you that every symmetric matrix can be diagonalized. So C is diagonalizable. And in particular using what? In particular using an orthogonal transformation. I know that the matrix C being matrix C is a real symmetric matrix. So therefore it is diagonalizable. It is diagonalizable. Now think about this matrix D and C. Do you think that this matrix is diagonalizable? If I'm saying, let us say, just let me write. Do you really think that this matrix C, which is given by 1, 1 minus iota, and here you have this 1 plus iota, and here you have this 0, is C diagonalizable? Is C diagonalizable? Yes, indeed it is diagonalizable. Why? Because C is what? C is clearly a Hermitian matrix. So C is clearly Hermitian. C is Hermitian, and every Hermitian matrix is diagonalizable. implies diagonalizable. So it is diagonalizable. So matrix C is diagonalizable. Okay, so all these questions may come up in your exam also. So please kindly understand all these things. We'll do a little more things tomorrow also. But today, let us try to do a few more things, uh, and then it would be easy for us. Okay, we'll do a few more things. Don't worry, we'll do a few more things also. But acha, what is the use of? I'll let you know. Just give me that. Okay. Now try to do a few more questions. Try to do a few more questions and properties regarding diagonalizability. So this is some important stuff regarding diagonalizability I'm going to write. Okay. Now just think about all these things, what I'm stating. Okay. Okay. Let me just help myself. Just give me a minute. Okay. Okay. So we have done the diagonalizability to a great extent till now. Now we are doing a few questions. Now we are doing a few questions. Okay. So regarding similarities, now regarding some points regarding similarity, some questions regarding similarity. The first question that I'm asking you is, first, is matrix A given by 1, 2, 0 and 3, and B is equals to 3, 0, 1 and 2. Are they similar? Are they similar? So is matrix A similar to B? Is matrix A similar to B? So indeed it is. Why? I told you this morning itself, if the matrices are similar, the first check that you should do, if the matrices are similar, if the matrices are similar, then their determinants are same. Then their determinants are same. Then their determinants are same. Okay, in this morning itself we've done that if the two matrices are similar, then they will have the same characteristic polynomial, and if they have the same characteristic polynomial, uh, so like I told you, no? So if you remember, what did I do? I wrote that B is equal to P inverse AP, right? And then I took the determinant of, let me take determinant of P. Determinant of P would be equals to what? Determinant of P inverse, determinant of A, and then determinant of P. Determinant is a linear transformation, so I'll do this determinant of P inverse. You can say what I will do. determinant of P inverse is determinant of P raised to power minus 1, determinant of A, and then there is determinant of P here. So what I'll get? I'll simply get determinant of A. So determinant of B is equals to determinant of A. So if the matrices that are given to me are similar, so if the matrices are similar, then they are bound to have the same determinant. So let us first think that whether the matrices are similar or not. Why I am guiding you this way? Because see, if at all in exam you are you find this P inverse AP, this is a long approach. First check is just see the determinant. The first check is just see the determinant. So what is the determinant? The matrices are similar. I told you now, if the characteristic polynomial are same, it does not imply that the matrices would be similar. If the matrices are similar, then the characteristic polynomial will be same. So please remember, first check that you should do is by checking the determinant. If you find that determinant are equal, then okay, then you may think of something else. But if determinant are non-equal, then why to check further? Why to check further? Are you getting my point? I think there is only one student right now. Are you getting my point? So these two matrices are not similar. Okay, this is something that you can see. These are not similar matrices. Okay, good. Now just do this question. These are not similar. Good. Now try to do this question. Okay. Okay. Now let us try to do this question. What do you think about this matrix? Okay, what do you think about these matrices? A is equal to 0, 1, 5, 3, and then B is equals to 1, 2, 4, and 3. So straightforward, the first thing that you should check is what? First thing that you should check is what? The first thing that you should check is the determinant. So if the determinants, what is determinant A? Determinant A would be, I think, minus of 5. What is determinant of B? Determinant of B is also minus of 5. Okay, so determinant is same. Now let us see. If the determinants are same, if the matrices are same, then remember the eigenvalues are same. Eigenvalues are same. That I told you in the morning. Plus, in fact, their algebraic multiplicities are also same. Their algebraic multiplicities are also same. So what does it imply? If their algebraic multiplicities are same, their eigenvalues are same. So let's say it has eigenvalue lambda 1, lambda 2. It has eigenvalue lambda 1 and lambda 2 with I think let's keep it simple with 1 1 multiplicity. Then lambda 1 plus lambda 2 of A and lambda 1 plus lambda 2 of a matrix B will be same. So I can write that the trace would be same. Trace of both the matrices must be same. Trace of both the matrices must be same. So if at all there are, see, if at all two matrices are similar, then traces must be same now. Because if the traces are not same, then it will contradict the statement that eigenvalues are same. So you can clearly see that here the trace of A is equal to what? Trace of A is equal to what? 3. Here you can see that trace of B is equal to what? Trace of B is equal to 4. Clearly trace A is not equal to trace B. It implies that your matrices are not similar. So A and B are not similar. So small concepts, if you're going to keep in mind, then things will be easy for you. What do you think about this matrix? Let us say A is equal to minus 1, 6, minus 2, and 6, and then you have this B matrix given by 3, 0, 0, 2. Now here, let us first try to take the determinant. So what would be determinant of A? Determinant of A would be, I think, 6. What would be determinant of B? It is also 6. So determinant is same. In fact, you can see the traces are also same. So trace A is equal to trace B. Now next, now let us try to find what? Now let us try to find okay, so the traces are same. Okay, so traces are same. If traces are same, then we can formulate, I will write, then we can formulate that both will have the same characteristic equation, that is t square minus, if you remember, If I have to write a quadratic equation, I know sum of roots here, and then times t, and then you have this product of roots. What is product of root? Product of root is this determinant, and what is sum of root? It is equals to trace. So it is 5t plus 6. So both of them have the same characteristic polynomial also. Both of them have the same characteristic polynomial also. Okay, now uh, let us try to find what would be the eigenvalues of A. What would be the eigenvalues of A, for which I will find this A minus lambda A equal to 0. That will give me, I should write 6 minus lambda. So lambda minus 6 into lambda plus 1 minus of plus of 12 equal to 0. It will give me lambda square minus 5 lambda plus 6 equal to 0. So you are getting either lambda is equal to 2 and lambda is equal to 3. So clearly there are two distinct eigenvalues. Clearly there are two distinct eigenvalues of A. Since I say there are two distinct eigenvalues of A, what does it imply? It implies that A is diagonalizable. Indeed, A is diagonalizable. A is diagonalizable. And if A is diagonalizable, then there indeed exists a P such that P inverse AP would be equals to what? Would be equals to B. So clearly A and B are similar. Is that clear? And in order to find this A, I have already taught you ways that you have to make an eigenvector, you have to find eigenvector, then make a matrix out of that. But clearly A is diagonalizable. So if A is diagonalizable, then P inverse AP would exist indeed. So I can say that B would be similar to A, or A would be similar to B, isn't it? Please let me know in the comment section if you are following this particular thing. If you are not able to follow, please let me know then also. Okay. 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 So is that fine? Or should I move ahead now? Okay. So try to do this question now. Okay. Try to do this question. Do you think that these two matrices which I'm giving to you, that is matrix A, given by minus 1 6 and minus 2 and 6, and B is given by 1 2 minus 1 and 4, are they similar to each other? So it's quite easy to find that this one is, I think, the same one, same as the above. So I know that the trace of A is what? Trace of A is simply 5. Trace of B is also simply 5. What is determinant of A? Determinant of A is simply 6. Determinant of B is also simply 6. So clearly the characteristic polynomial will be t square minus 5t plus 6 equal to 0. Oh, sorry. If you want to write it in lambda, so it will be lambda square minus 5 lambda plus 6 equal to 0. So you have two distinct eigenvalues. If you have a two distinct eigenvalues, it implies that A and B are both diagonalizable. Are both diagonalizable. If they are both diagonalizable, then there will always surely exist a non-singular matrix which can diagonalize A and which can diagonalize B. So let's say there exists a non-singular matrix S which diagonalizes A. And what would be the diagonalization? If it is diagonalized, then I can say that this will become the a diagonal matrix which is 2, 3, 0. And similarly, there would exist some non-singular matrix P such that P inverse BP will also be equal to what? 2, 3, 0, 0. Is that clear? So indeed, I can write that my S inverse AS would be simply equal to B in P inverse BP. And I can write what? I can take like what I can do. I can multiply with P inverse. I can multiply with what you can say P. I'll get S inverse A, S, and then I'll do a P inverse, and here I'll get B. And what am I getting? I know that this particular thing I can write as U. So I'm getting that U inverse A U is equal to what? B. So clearly A is related to B using a similarity transformation. So it implies that A is similar to. Is that clear? I hope it is clear till now. Now let us do a few more questions and then I'll finish this lecture off, and then we'll meet tomorrow, and a day or two will be more required for your matrix algebra, and then we'll be finished. Then we'll finish it off. Okay, so try to find me this. I think this will be an interesting question for you. Try to find me that if A is given by, if A is given as, if A is given as 2, 1, 1, 2, then what would be A raised to power 8? What would be A raised to power 8? What would be A raised to power 8? If A is 2, 1, 1, 2, then we have to find A raised to power 8. See how to go about it. Let me help you with this. So what I'll do, let us create a matrix P which is related to A by similarity transformation. Okay, so let's say B is equal to P inverse AP, or I can say that A is equal to P B P inverse. Now if I take A square, what I'll get? A square is what? I'll get P B P inverse, again P B P inverse, and eventually I'll get it as B, and I will get it as, this is identity, so I'll get P square and then P inverse. And if I continue likewise, I'll get that A raised to power 8 is nothing but it is equal to P B raised to power 8 and P inverse. Is that clear? What would A raised to power 8 would be nothing but it is P B raised to power 8 P inverse, right? What is B? B is a diagonal matrix. B can be a diagonal matrix here. B can be simply a diagonal matrix. And diagonal matrix what? Diagonal matrix comprising of the eigenvalues of A. So B would be what? B would be simply, I think what will be the eigenvalues? Eigenvalues of A, I'm writing it here. Eigenvalues of A would be simply 2 minus lambda whole square minus 1 equal to 0, and it will yield me lambda square minus 4 lambda plus 3 equal to 0, So it will give me 1 and 3, or 3 or 1, whatever suits you. So let's say this will be your matrix B. This is your matrix B. And whenever you reduce it to a diagonal matrix, please remember, if I would take b raised to power 8, it is equivalent to writing 3 raised to power 8, 1 raised to power 8, and 0, 0. Simple. You can do it on once you can verify yourself also. If you have a diagonal matrix and if you want to take the power of that diagonal matrix, the power actually comes over the diagonal elements. So this is one thing. I think 3 raised to power 8 is 6561, and here you have 0, here you have 0, here you have 1. Okay, this is clear. So b raised to power 8 we have found. Now in order to find this p, what we have to do, we have to find the eigenvectors corresponding to a. I have to find the eigenvectors corresponding to a, and I have already found that lambda is equal to 1 and lambda is equal to 3 are two of the eigenvalues. So to if I use 1 as the eigenvalue, so 2 minus 1 is simply, I think, 1. So what I'll get? I'll get 1, 1, 1, 1, and here I'll get x1, x2. And here I will get what? Here I'll get x1 is equal to minus of x2. Okay? And so the eigenvectors would be 1 and minus 1, right? So for lambda is equal to 1, the eigenvector is 1 and minus 1. And for lambda is equal to 3, the eigenvector would be minus 1, 1, 1, minus 1. So here you have this x1 equals to x2, which implies 1, 1. So eigenvector corresponding to lambda equal to 3 is 1, 1. I can normalize both of them by using 1 over root 2. So clearly I know that my P, the matrix P, I can write as 1 over root 2, 1, 1, 1 minus 1. Right? This would be my matrix P. If I know my matrix P, I know b raised to power 8. So I can do 1 over root 2. And I have to find a raised to power 8. Don't forget, I have to find a raised to power 8. A raised to power 8 would be 1 over root 2. P, that is 1, 1, 1 minus 1. Then I have this b, which is given by 6, 5, 6, 1, 1, 0, 0. And then I have this again 1 over root 2. And then I have again 1, 1, 1 minus 1. So this is 1, 1, 1 minus 1. So this will give me 6, 5, 6, 1 here. This will again give me 6, 5, 6, 1 here. I will get a 1 here, I will get a minus 1 here. And if I again calculate 1 upon 2, this will be 6, 5, 6, 2. This will be 6, 5, 6, 6, 5, 6, 0. Then I will get again 6, 5, 6, 0. And again I'll get 6, 5, 6, 2. Okay. So eventually a raised to power 8, I can write it as divided by this, I think 32, 8, 1. So 3 to 8, 1. Here you will get 3 to 8, 0. Here you will get 3 to 8, 0. Very strange answer, but okay. 8, 1. Okay. So this is how you got an answer. Is that clear? I hope all those who are attending the class must have got this particular question. Please let me know if there is any doubt. Please let me know if there is any doubt, so that I'll give you another question. Sorry. I hope it is clear till now. Okay. Okay. Now you see, one of the question. It's not always necessary. Let's say I'll help you with the example, and then we'll see. I'll help you with the example. So the question, this particular question was asked in JEST examination. Okay, and the question said, consider matrix A of 2 cross 2, and the matrix A is given by what? Matrix A is given by 1, 13, 0, and 1. And then question was asked, what is a raised to power 27? What is a raised to power 27? This was what it was asked in JEST exam. Now, in order to do this question, the first thing I always say that whenever you are doing these questions, try to see that whether your matrix is diagonalizable or not. That is the first thing that you should see. because only if matrix is diagonalizable then we can apply this approach that I have stated above. But you see here clearly, if I find if I find a minus lambda I mod whole square, what am I getting? I'm simply getting what? I'm simply getting 1 minus lambda whole square equal to 0. Clearly, a does not have uh, distinct eigenvalues. Does not have distinct eigenvalues. Also, that you can see that the minimal polynomial, if you want to make that also, let's say if my minimal polynomial is a minus lambda I, that is the only a minus I. Let us see that whether it works or not. So it will be 0, 13, 0, 0. So it's not even what you can say, it's not even the null matrix. So clearly this is not a minimal polynomial. It implies the minimal polynomial is this, and if this is the minimal polynomial has power 2. So if minimal polynomial is only in terms of linear factor, only then we can have, only then we can say that our matrix is diagonalizable. That implies a does not have, a is not diagonalizable. In short, I can write that a is not diagonalizable. And since A is not diagonalizable, I cannot apply the above approach. I cannot apply the above approach. I hope it is clear. I cannot, I should write. So therefore, the above approach will not be valid. I'm just writing therefore. The above approach will not be valid. Okay. Now it gives you a certain sense of thought keep what to do. See, whenever you have these kind of thing now, whenever you have these powers, another thing that you can use is the Kelly-Hamilton theorem. So another thing that you can use is the Kelly-Hamilton theorem that has not gone. Okay, so there it's still there. So please do remember, it will be lambda minus 1 whole square. This is your equation. So it is lambda square minus 2 lambda plus 1, isn't it? This is, I think this is what is your characteristic equation. If this is the characteristic equation, then I can write that my lambda square would be equals to what? It would be equals to 2 lambda minus 1, and I know that the matrix satisfies its characteristic equation. Matrix also satisfies its characteristic equation by Kelly-Hamilton theorem. So a square would be equals to what? A square would be equals to 2a minus of I, right? So it satisfies its characteristic equation, right? What do you think would be lambda cube? So lambda cube will be equals to what? Lambda cube will be equals to 2 lambda square minus lambda. And if I write lambda cube is equal to what? It is 2 times, I think this is 2 into 2, this would be 4 lambda minus, oh, lambda square now. So what is lambda square? It is 4 lambda. Uh, just give me a minute. Huh? So if lambda cube I'm writing, lambda cube will be what? I'm multiplying lambda throughout. If I multiply lambda throughout, and instead of lambda square, if I use this, so instead of lambda square, if I use this is 4 lambda minus 2 and minus lambda, right? If I'm not wrong. So I think lambda cube I will get as, so lambda cube I'm getting it as 4, 9. This is 3 lambda minus 2. What do you think lambda 4 would be? Just inductively I'm trying to create some sequence kind of thing. So lambda raised to power 4 would be equals to what? Lambda raised to power 4 would be equals to 3 lambda square minus 2 lambda, and it would be 3, so it is 6 lambda minus 3 minus 2 lambda, so it is 8, no, it is 4 lambda minus of 3. Okay, okay, so I hope it is clear that uh, that let's say if the power is of 2n here, what I'm getting 2n here, and here I'm getting 2n minus 1. Is that clear? Or in general, if I take this also, lambda cube also, if I'm taking n in general, what I'm getting? I'm getting n lambda here and minus of n minus 1, right? So if I use n is equal to 27, what I'm getting? Lambda raised to power 27 would be equals to what? It would be equals to 27 lambda minus 26, right? Or I can write that a raised to power 27 would be simply 27 times a minus of 26. This is by uh, your Cayley-Hamilton theorem. And what is your a? Just don't forget your a is equals to what? It was 11301, 11301, 11301. So you will get here. Uh, so a raised to power 26 will be 27a minus 26i, and it is equals to what? It is 27 here, and here you will get again I think what was it? Just give me a minute. Okay, what was it? It was 11301, 11301. Okay, it is 11301. So I'm writing 1, I'm writing 13, I'm writing 0 and 1. So what it would, and minus 26, 2600. This is the, okay, this is the quite sure also. Okay, so what we'll get here? We'll get 1 here. What is 27 into 13? 91, 9 carry 13 into 6, 351, right? And here you will get simply 0, and here you will simply get 1, because this is minus 26. So this is an answer for a raised to power 27. So please don't, it is not always necessary that whenever a power question, a power of a matrix comes, you have to do a diagonalization only. See, if it is diagonalizable, do it. If it is not diagonalizable, then you cannot help yourself. You will have to do this only. I hope it is clear till now. Okay, one other question again. Let us try to do this also, and then we'll conclude the class. Okay, this is the last question. The question from TIFR says that this is the matrix given to you: 1, 1, 0, 1, 1, 1, 1, and here you have 0, 1, 1. It is related by similarity transformation to which of the following matrices? Using similarity transformation, it is related to which of the following? Option number 1, it was given 1, 1, 1, 1 minus 1, 1, and there you have 1, 1, 0. Option number 2, it was given 2, 1, 0, 1 minus 1, and again you had a minus 1, and then you had 0, minus 1, minus 2. Option number C, it was given to you 1, minus 1, 0, minus 1, 1, and 1, and 0, 1, and minus 1 here. And option number D that was supplied to you was 1, minus 1, 0, and minus 1, 1, 1, 0, 1, 1. So which of the following do you think that is, so the matrix is related, this matrix is related to, uh, is similar to which of the following matrix? Is similar to which of the following matrix? Just take this as an example. I'm not writing the exact question. The exact question was that the similar, that this matrix that is given to you, that is 1, 1, 0, 1, 1, 1, 0, 1, 1, is related via similarity transformation which with which of the following options, that is A, B, C, D, is given to you. The first thing that I taught you just a little bit before, just a little bit ago, that whenever you have to find, whenever you have these questions regarding similarity, try to find the trace and determinant. Okay, try to write the determinant. So what would be the determinant here? So determinant would be, it would be 1 minus 1, 0. Here it is. Okay, so determinant I feel is -1, right? Determinant is -1. I hope it is clear that let's say this is your matrix A, the determinant of A would be -1. What do you think the trace of A would be? So trace of A would be 3. Trace of A would be 3. So I know that I have already stated that if the matrices are similar, then the eigenvalues will be same. If eigenvalues are same and of the same algebraic multiplicity, then the determinant and the traces would be same. And if this is the case, let us try to conclude this particular thing. See, this particular thing has a trace 0. Forget about it. This particular thing has a has a trace -1. Forget about it. Okay, this particular thing has a trace of 1. Forget about it. This particular matrix has trace 3. And if you want to find the what you can say, if you want to find the determinant also, this is the trace and determinant are same. So question says can be. So yes, this can be. Yes, indeed it can be. Now don't sit in the examination finding P inverse AP. That would be, I think, disaster for you in the exam. See, already it is given that this is similar to some matrix. Some matrix. So if it is similar to some matrix, then obviously these three cannot be the case. So obviously these two can only be the case. And now it has already been given that A is similar to which of the following matrices. So like D should be the answer. I hope it is clear. Okay. So I hope you've got much of these insight in particular, what you can say, in this particular section. We'll try to finish our matrix algebra in a couple of days, and then we'll start with some physics, and alongside we'll run with the linear algebra course. A linear algebra course is very essential for your quantum mechanics. If you do it in detail also, then it's not going to harm you as such, because see, if you have a very strong hold of linear algebra, then as I told you, even if you have a little bit lesser insight in quantum mechanics, like physically, which is very difficult also to have that kind of insight, then also things will work out for you. Then also things will work out for you mathematically. Okay, so I hope that you'll join us in the lecture tomorrow also, and probably a day after. That will be the maximum matrix algebra that we can do. Okay, till then, take care. Bye bye.